Welcome back everyone to our Calculus 3 class notes. We are on example 66 here on page 70 and of section 14.7. So I just have another quick show me example of some functions or surfaces with interesting saddle points. So if I were to graph this guy, you can see a nice saddle point right in there. And here is a function, a surface as well that you can imagine is saddle point right in here. So it's not a minimum or maximum. If you look at it in one direction, it looks like a minimum. If you look at it underneath, it looks like a maximum. So you just have to kind of understand that these are not minimums or maximums, sort of the equivalent of inflection points for functions of one variable. Okay, now, sometimes it's not so easy like we did in the example where, let's see, take you back there real quick, where I was looking at this example, and I could easily see by the shape of this paraboloid, because we can graph those real quick by hand, that this value had to be the minimum, a local minimum of that function. Okay, so what we need to do is, it'd be nice if we had another test, and we do. It's called the second derivative test for local extreme values. So suppose f of xy and its first and second partial derivatives are continuous throughout a disk centered at AB, and partial of f with respect to x at AB is equal to the partial of f with respect to y at AB, and they're both 0. If we call this discriminant, we usually given the notation capital D because of the word discriminant. It's actually a 2x2 determinant to help us remember what it is. Some people have called it the Hessian as well. But this discriminant is this 2x2 determinant, so it's f sub xx times f sub yy minus f sub xy times f sub xy, or f sub xy squared. So the second derivative test, the theorem here says that f has a local maximum at AB if the second partial with respect to x is less than 0. So that's equivalent to saying, okay, we got a function that is, think about the second derivative of a function of one variable being negative. That would tell you you have a concave down type function. So similar here, second partial with respect to x less than 0 looks like it's going to be a local maximum as long as that discriminant is also greater than 0. So I'm not going to do the proof behind this, but essentially what this discriminant does is it just looks in different directions and determines that you can't have it going up in any of the other directions. So as long as that discriminant is greater than 0 and the second partial of f with respect to x is less than 0, we're going to have a local maximum. If the second partial of f with respect to x is greater than 0, you can think of that as sort of being a concave up area. That would mean we're going to have a local minimum. And as long as that d, that discriminant, is greater than 0, that verifies that we do have a local minimum. If you ever work out the discriminant and you get it to be negative, that tells you that you have a saddle point at AB where the first partials are equal to 0. It doesn't matter what the second partial with respect to x is. If that discriminant is less than 0, you have a saddle point there. If you ever get the discriminant equal to 0, the test is inconclusive. So we must find another way. For us, that should never happen. And it's harder to find other ways. So for us, that should never happen. Okay, so let's look at an example here, example 67. Find the local extreme values of these two functions. So let's look at the first one. By the way, both of these, the domain is the entire xy plane. We're not talking about any boundary points. So this first one, take the partial of f with respect to x. I get y minus 2x minus 2. Set that equal to 0. Take the first partial with respect to y. I get x minus 2y minus 2 equals 0. So they both have to be equal to 0, so I have a system of two equations with two unknowns. There's multiple ways to solve it. You can solve that and you see that x equals minus 2 and y equals minus 2. So that point, xy minus 2 is the only point where a local extremum could occur. So now we're going to do the second derivative test. So I check the second partial of f with respect to x, and I just get minus 2. So that means the second partial is negative, which means that as long as the discriminant is positive, I have a concave up function there, so that would be that I have a local minimum. So now we got to get f sub yy and f sub xy, plug them into the discriminant, and I see that yes, indeed, the discriminant would be 4 minus 1 is 3, which is positive. So since the second partial of f with respect to x is negative and the discriminant is positive, there is a local maximum, right? Concave down, local maximum at -2, with a value of f of -2, which is 8. Just plug in -2, -2 for x and y into the function and get 8. So we can do a similar thing with b here, and I thought it was a cool looking function based on the results, so I graphed that with GeoGebra for you. Okay, you can see that we have a local maximum here, and then we have a saddle point here. Now let's see how the mathematics works out. So the domain of f, entire xy plane, no boundary points. Take the partial of f with respect to x. Looking back at the function, I get minus 6x plus 6y, set that equal to 0. Tells me x has to be y. Take the partial of y with respect to 0. I get 6y minus 6y squared plus 6x equals 0. But I know that x equals y, so that's another 6y. So that's 12y minus 6y squared equals 0. Factor out 6y, I get 6y times 2 minus y equals 0. So y is equal to 0 or 2. So that means that x is also equal to 0 or 2. So x is equal to y, so we have two critical points. When x is 0, y is 0, and when x is 2, y is 2. So two critical points. So we're going to check the second partial. Second partial with respect to x is negative. So that's always negative. That would mean that both points could possibly be local. This would make it concave down, local maximums. But to see what we have, I have to check the discriminant, which is this guy. So I need the second partial with respect to y, which has 6 minus 12y. So that's going to be different depending on what y value we plug in. F sub xy is 6, so that will always be 6. So at the point 0, 0, then y is 0, so f sub y is 6. I plug it in, I get minus 36. Minus 36 is minus 72, which is negative. As soon as I have the discriminant being negative, I know there's a saddle point at that point. So there's a saddle point at x equals 0, y equals 0, and f of 0, 0, which is also 0. Right? Plug it back in there. F of 0, 0 is also 0. Okay, and then at the point 2, 2, still have the second partial negative. Now f sub y is going to be 6 minus 24, or minus 18. And f sub xy is still 6. So now I get minus 6 times minus 18, which is 108. Minus 36, that's 72. So the discriminant is positive. So since the second partial with respect to x is negative, it means I have a concave down function there. And the discriminant being positive means yes, it's down in every direction. So that means that we have a local maximum at 2, 2, f of 2, 2, which is 2, 2, 8. So that's this point right here. So saddle point here, local max here.